Okay, so of course, creativity is a very broad concept, right? It's something that gets looked at quite a bit in engineering design, especially when we're doing conceptual design. So we're doing concepts. We're thinking about general working principles that we want to use. And creativity is a skill that you can say, you know what, it's a soft skill. It's the ability and willingness to consider solutions that are outside of the norm, that are novel, that are interesting, that you wouldn't think of if you just systematically approached something, right? So all of us have examples of creative design in engineering, right? So I was giving the door latch or the doorknob assembly earlier. Creativity was going from a much more complex design to a simplistic design that works exactly the same. There's really no difference once it's assembled, except that design-wise, there's a lot of difference, right? So concept generation is coming up with design alternatives. Concept generation is a task where creativity becomes essential. So, like I said, it's an abstract concept. So it relates to the ability to come up with substantially new ideas or solutions. And we can actually effect fundamental changes in a product or a system if we are ready to be creative, right? So many solutions have gone from, I'm sure you've seen the evolution of some of the rocket engines over time. And then you see we simplify things, we come up with new solutions and so on and so forth. So people will say some people are creative and some people are not. And we've found that creativity is not innate, it can be learned, right? So people can actually, over time, develop the ability to come up with creative solutions. Anybody work with genetic algorithms here in optimization? So one of the ways, simplistically, even later in the lectures, I'll talk about genetic algorithms in a little bit more detail. But one of the ways it works is it mixes and matches part solutions or solutions to sub-problems in many different ways. And when it does that, it's able to come up with new novel solutions itself, right? Just like we do in nature, right? We have, let's say in reproduction, the genetics combine, and then we have newer and newer individuals that are over time evolved to have better and better traits. So if you think of flying, that's a pretty complex activity that some animals and insects are able to do. If you go back to the evolutionary process, scientists say that flying has been invented by nature multiple different times using different pathways. Okay, it means that this solution can be found over and over again using this idea of mixing and matching. And then you realize when you come back to the genetic algorithm world where you start thinking, okay, well, even though it's not an innate, it doesn't necessarily have to be an innate skill. It is a skill that, so it can be learned, and you can have a systematic way of coming with creative solutions, right? So we talk about creativity from a novice and creativity from an experienced engineer. Okay, so somebody who's not experienced with a certain design or a certain application area, you would see that they'll have a lot of new interesting ideas, right? What is the challenge with their ideas typically? Most of their ideas might be infeasible because they don't fully understand how the system works. They haven't really gone through the process of. So a new engineer has a lot of interesting new ideas, right? You come to an engineer in the field, a lot of you will, if you go to industry, you will see, oh, why don't they do it like this? Why don't they do it like that? Oh, I have an idea for doing this, right? And many times, oh, that doesn't work. Oh, that's dangerous, or right? So those kinds of things can happen. And it's a double-edged sword, right? So if not having enough experience gives you the yeah. Everybody can still hear me, right? So not having enough experience or sometimes helps you in coming with new ideas because you're not constrained. You don't think about, you're not, so we say, jaded by your experience. One example that comes to mind always when it comes to this is, I don't know if you've heard of the movie Citizen Kane. Okay, so Citizen Kane was a movie made in, I think, 1941, directed by Orson Welles. He was, if I remember correctly, 24 years old. That was his first movie. And even now, it's considered the best movie ever made. Okay? So one of the things that, when he was interviewed, they asked him, how were you able to make this movie that is considered one of the best movies ever made when you were 24, and he said ignorance. There's no confidence to match it. If you don't know much about something, there's nothing holding you back. You start questioning, and that's why he was able to do so many interesting things with the movie. Obviously, it's one of my favorite movies, so if you get a chance, definitely watch it. So there's creativity from a novice, right? When it works, it's amazing. Okay, and when it doesn't work, of course, it's disappointing, but we should take it as a learning experience. You should not think that, okay, I had a bad idea, now what? You should say, okay, well, I'm expected to have bad ideas now because I don't understand the entire working of the system. And that's something that's going to have, the more complex the system gets, the more of these ideas you will have. Because even if you thought of the subsystem, you may not have thought of all the different interdependencies with different subsystems, right? So you might make a change here thinking that I improve this subsystem, but I may have made something else worse, right? So there's an example, I wouldn't get into much details, where they were just changing a structural element in a plane, okay? And they were able to reduce, either with new materials or new design, part of a plane. They reduce the weight of it, right? And in aerospace, weight is everything. Every pound saves you 5 pounds, as they say, right? Because reducing weight, you don't have to carry the fuel to carry that weight. Everything goes smooth after that. But so you would think that anybody that can take a structural element and then reduce the weight without compromising strength is a great thing. Except it's not a great thing. It's not always a great thing, I should say, because in that particular case, the location of the center of mass or center of gravity of a plane should be in front of the aerodynamic center. That's not a trivial thing. You change it. Now, the flight control software, everything has to change. The entire plane starts acting differently. Okay? Going back to our 737 example, those are the kind of things happen. Even if you made the plane lighter, you change the weight distribution. You change the location of the CG of the plane. Now the plane handles differently. Every control input that you have has to be modified based on the fact that the plane has different stability characteristics. So you would think that, oh, I made this lighter and I made this better, but you caused system level issues over there. There's other issues also, I think, that came from it was, I think the natural frequencies and all those things changed of certain, so it led to cascading other system level changes, which you wouldn't think, but you should embrace that idea. So the idea is not to say, okay, well, we should not make planes lighter. That's not what we're saying. We should make planes lighter only when we understand the system enough and or involve the decision makers in other subsystems, involved with other subsystems, so any change that you make can be accommodated. So if those people knew about what change you're making, they can change the flight control software, they can make other changes to the plane and go from there. Okay? So, and then new engineers should embrace this experience, that, don't get disheartened. But also be careful. Don't start implementing ideas without telling people, right? So, oh, I made it cheaper, now I'm going to implement it. No, discuss it. Discussing with experienced colleagues is important. Yes?
Is there any correlation between creativity and design thinking?
Creativity and design thinking? Well, yeah, design thinking is, creativity is a sub-part of that, right? So creativity helps you with coming up with better and improved designs. But again, we should embrace it, but I don't know if we can necessarily measure it. So creativity is something as an abstract concept that should be encouraged. Thinking outside the box, as they say. It's as a novice engineer, you should embrace the idea in your designs. And as an expert, so that's the next point that we have here. As an expert, you have a different look to creativity because you're creating on top of your already good understanding of the design. So those creative steps have immediate benefits because they are already at the boundary of what's considered a good design. Okay, so any improvement that you make quickly shows. In the case of a novice, if their design thinking is let's change things and see what happens, versus we know what happens, changing this in this way will make things better. So like I said, they're better at suggesting incremental changes. Experts are. They can figure out, if you tweak this, it's going to get better. Right? An example comes from when I was in industry. Well, we had a vacuum pump, and then it had a port, aluminum port that that was just shrunk fit. So you could you could remove it, but you had to remove it without damaging the port. Now it's made of aluminum. You can scratch it very easily, and then the seal would no longer work. So I was thinking of different ways to do it, and then there was a senior guy, and then he came with a contraption, a clamp, and then the clamp on the periphery had threaded holes. So if you just screw a few screws through them, then you can just gently push it out or pull it out, depending on your perspective. And it was wow, we had no idea how to do this, and he was able to do it because he knew the constraint that you cannot scratch the surfaces, otherwise it wouldn't seal. He may have done it in the past before. Plus, he also knew that something like that existed in the inventory, right? I didn't know that such a part existed. So that there was an approach to it which had a quick, immediate solution. It's not, in hindsight, it's a simple idea that anybody can think of. But I didn't think of it because, I don't know, I think something like that existed. To fabricate something like that would be more challenging than just come with some other ways. So that's the difference between how novice and experienced engineers think about creativity, or should think about creativity. So lack of creativity stems from artificial constraints that human mind imposes on the solution. We think that certain things should not be done. And that's the idea, is to get away from that, right? So we ask questions, are there fundamental issues that need to be addressed before improvements can be made to a product? Then there may be no quick improvement possible, right? So nature imposes constraints. Like nature says, you can't do this. If you can't do this, then there's no, in all of your engineering, you're learning things like this cannot exceed that, right? Okay, well, that's a physical law, right? We talk about efficiency of heat engines, and then there's maximum efficiencies you can get out of certain heat engines. That's law. So don't try to break those. That's not going to work, right? For hard drives, used to be certain gigabytes before. Suddenly, we had some fundamental new understanding of how hard drives could store information, and now suddenly there was an explosion in the capacities, right? So that's something you just cannot do by tinkering with it. You have to solve fundamental problems. If there's fundamental problems, then I guess systematic solutions are the only ones that are going to work. For example, or you can trying to do an incremental change, right? So you can say, okay, well, you can improve a product, and there's millions of examples of this, right? That you can think of improving that. Why don't we just do this, right? Long time ago, people would use flashlights, the screen light, to see things in a dark room. So why don't we just add a flashlight, and then things were easier, right? Ask yourself if you understand the functioning of the product enough. So you can think that you can do something, and again, going back to our discussion of novice engineers not understanding the working of the system enough, is that I can install, so in the scrubber example we'll cover later, I can install a lighter motor here and then it'll work. Well, no, you don't quite understand. The objective of that is not just to pump water, but it's also to create enough pressure over there so that it accomplishes a second task, right? So if you don't understand the working of a product enough, you might run into these kinds of situations, right? So I think this is a real problem that we had. We had space constraints, so we thought we'll just put a small motor there, but then, of course, it wouldn't accomplish the purpose. Many times manufacturers would say, don't repair your products, it'll void the warranty. For this reason, you might think you're making a change, but you're actually making it worse, or making it more dangerous. So they say, don't repair products. And many solutions are a result of somebody backtracking to the essential function, right? So sometimes we get anchored to a given architecture, given product. So this is the product we have, and we can change this. go back to the original purpose. I mean, we have all these examples of slide rules versus calculators. The original purpose of the product was this. Why am I doing this? Let's think of a better way. So, a related thing that from the whole genre of things of creative design, concept generation is axiomatic design. And again, all of these are research areas in their own right. People have done a lot of work in these areas. I'm just trying to introduce you to some of these concepts that when you're doing concept generation, conceptual design, you should think about these things. These are guiding principles that you can use. So we talk about creativity. It's a guiding principle. We cannot really come up with a theory, mathematical theory of creativity. That's not going to happen anytime soon anyway. So another thing is axiomatic design, right? So each product and each design is different. Okay. So if each product and each design is different, then what similarities exist? We can never study product design. We can never study systems design, right? So if we start going back to our first lecture, I kept saying domain independent skills. Develop skills that are domain independent that you can apply to a design of a water bottle. You can design it you can apply it to the design of a personal computer. And that's what domain independent knowledge is. And that's where this whole idea of axiomatic design falls. That, like I said, it's not something that we can have a mathematical theory for, but definitely it serves as a guiding principle. So the first one is maintain the independence of functional requirements. So functional requirements should generally be addressed independently of each other and minimize the information content of the design. So information content of a design roughly translates into how much information is required to completely manufacture a product, and this should be minimized. Okay. Can one of you try to elaborate on these? First one, maintain the independence of functional requirements. Remember when we talk about customer needs are addressed by functional requirements from the product, right? So functional requirements are features of the product or the system that help us address customer needs. This one's saying keep them independent.
So like each functional need should be like each customer requirement should be addressed by a different functional need.
We're not talking about customer need. Customer needs are already mapped to functional requirements. We're talking about functional requirements themselves. One functional requirement should be addressed as much as possible independently of the other functional requirement.
There are aerodynamic requirements and there are structural requirements.
Did somebody give her a microphone?
There are both aerodynamic requirements and structural requirements, and also there could be safety requirements. But with contradicting to this first statement, we have we have some components that do both aerodynamic as well as structural functionality together. So I quite not sure if I agree to that point, maintain independence of functional requirements, but rather than how we are verifying it, definitely aerodynamic requirements are verified independently from the structural requirements verifying independently. So the verification process would be easier if we keep them independent.
Okay. So that's a great point. So your example comes from aerospace, right? Okay. So there's a couple of things I would say. That the aerospace, you work with a severe weight constraint, right? So some things you have to, to make an integral product, you have to combine multiple functionalities into one. So that's you working in a very different constraint than most products and most systems are. Okay.
But when it comes to requirements, every requirement should have its own way of verifying it.
Right. No, I see the point that you're making, but this is more general. But I would even contend, but look at engines. Engines are made and added. They're basically potted engines, right? So you basically add engines almost as a swap. You add one, add here. So as soon as there's modularity, you maintain the function. You separated the functional requirement of the rest of the plane with the engine, right? So it still applies, right? You are working with a specific product that has to have an integral architecture. So you're stuck with combining multiple functional requirements into one. But when you get a chance, you don't do it. When you get a chance with the engines, you finally said, if you remember old engines, some of them were embedded in the tail. That was a bad idea because now you've embedded an engine in a structural part, and repairing that engine was problematic. So we said, okay, that no more of 3 engine planes, only 2 engine planes, and then they're potted, and you can swap them out whenever you want. So I would still say that this is a very good, because this is the only thing that leads to modular products, right? And modular product, it should be our answer. If you could swap wings whenever you wanted and swap, you would love to have a modular design. You cannot do it because that leads to inefficiencies. But we've managed to do it in a computer, right? We take a motherboard from here, we add this card and add that card and that hard drive and this processor and this, and it works. So because we have completely separated the functional requirements. Visual, you do it. Storage, you do it. RAM, you do it. Right? So you're talking about a specific case, but in general, we cannot. These are general guidances. As I said earlier, we cannot say apply it to all cases. Another example to further exacerbate the violation of this rule would be space. Those are one-off things, right? You try to integrate as many things as possible because you can spend millions of dollars making it more reliable, and then you don't have your weight constraints. So you have that.
Yeah. Would you give a few examples in which it maintains the independence of functional requirements?
A personal computer.
Personal computer.
Right. So basically, you have a power supply. You can take out the power supply from this company, add another power supply. You take the motherboard out, leave everything intact, make the connections with the other motherboard, it'll work. Take the hard drive, add a different hard drive. People do it all the time, right? So it's a modular product. The storage, permanent storage, is completely independently done from power supply, which is completely independently done from this. Functionally, they have to interact in a system. We understand that, right? A lot of protocols that companies develop is what makes it possible. That there's a lot of, this kind of pin goes here, and this is the information protocol the hard drive will use with the motherboard. Once everybody agrees, then yeah, Seagate is just as good as Western Digital, which is just as good as Siemens and Samsung and things like that, right? So that's a victory of independence of functional requirements. We strive for it. In certain domains, we cannot do it, or we shouldn't do it, which is aerospace is a striking example of that. Mm-hmm. Yeah, you could do that, but you're losing. But you're losing modularity, right? And then the other thing is that some of those SoCs are not as capable as your personal computers, right? So, and then these are guiding principles, like I said. I mean, there's a lot of examples that. I mean, I'll give you one example right here. After I give you the Ford example, the Ford Taurus was one of the largest selling cars in the United States. Okay, and it was one of my favorite cars, to be honest. I think late 80s to mid 90s is when they made that car. Suddenly they went with an oval theme. Everything was oval in the car. The car looked like everything was oval. Even the control panels, the dashboard, everything was oval, right? And then they combined features, if I remember correctly, that should not have been combined. Now, if this module breaks, right, you have to take out the entire assembly to fix it. If that module fails, you have to take out the entire assembly to fix it. And there was a lot of those kinds of things. Like, I think it was the AC control switches or something was combined with some other control for the And there was a lot of other things wrong with the car as well. So it did not work. That model did not work. And actually, Ford Taurus lost the largest selling car title to Toyota Camry. That's when it happened. Right? I can give you another example, right? So it would be awesome if I could control everything in this room with one remote, right? So you have these switches here, and some more switches over there. And you have TVs and you have cameras and you have ACs and you have lights. It's very easy to think of, okay, well, how about I have a central module that communicates with one remote. I can turn on the TVs, I can turn on the lights, I can control the AC, I can control the shades, I can control everything with one remote. That sounds like a great idea, except when this remote fails or if I run out of battery, I cannot do anything, right? So, and then you have unnecessary issues every single time something breaks. So it's a good guiding principle when you're thinking of concepts. Can I make it independent? And then the other thing, even in your case, you would have to think about, if I could make it independent, I would, I should still strive for that, even though I know that I'm facing that constraint, right? Then I don't have to think about system effects that much if I have tried my best to maintain independence of functional requirements. System effects are only there because you have this issue. Sometimes you cannot. That's why aerospace systems are so complex and all that. I mean, one example I can give you is that large aircraft carry like hundreds of tons of fuel, right? 747 probably carries 200 tons of fuel. That's a lot of fuel. I just told you, you change something minor structurally and you change the location of the CG of the plane. How is it that you changed? Most planes are so heavy that they cannot land when they're full. I don't know if you know this, that planes are filled with fuel when they are about to take off, and they accelerate and then they take off. But if something happens, I'm sure you've heard of them jettisoning fuel for a long time. They pretty much throw the fuel away before they can land. Something needs to be done here. But he's not here. I think it should be stay in the call, right?
Yeah, it's safe.
Okay. So earlier I said minor weight changes the CG, bad things happen. Here, plane has 200 tons, plane that cannot land because most planes are too heavy. Their weight saving is everything. So their landing gear and structurally they're not strong enough to land. They have to first burn the fuel, get light, and they can land. Or if they land right away because of an emergency, they throw away the fuel to get lighter so they can land. Okay? But the fuel is distributed such that as it burns, it does not change or changes predictably the CG of the plane, right? Most of it is in the wings and all that. So you make sure that those things don't happen. So even in that case, you minimized the system effects by making it independent of that, right? So sometimes it takes some extra engineering, but it can happen. And the next one is minimize the information content of a design. That should be pretty obvious. But have you seen or heard about the Rube Goldberg machine? I don't know if you've seen, so somebody is sitting down to eat breakfast, right? And they press a button, and then and then the ball rolls down and hits something else, which triggers something else, and then opens the valve, and then that starts the stove, and something starts cooking, and then the robot picks it up and slides it. Really complex way of doing something very simple, right? I'm sure you've seen those ads and things like that, right? So the idea there is that's the opposite of what we should be doing in engineering. We should be making designs as simple as possible in terms of information content, right? So I mean, again, people will say that you can do it, but for a general product, you really cannot come up with a hard and fast rule, but you should say, keep it simple, right? Occam's razor, keep it simple, minimize number of parts, minimize number of things. I mean, in my systems engineering class, when I teach it full semester, I also teach design for manufacture, right? And if you read any of the books by Boothroyd in design for manufacture, you will see he says, minimize part count, minimize part count. He talks all the time about minimize part count, right? So, for example, he will say, okay, well, I have two things that need to be joined, screws. I join it with screws. He says, okay, well, how about plastic snaps? Just snap it into place. Guess what? If I don't have a part, if I can eliminate parts, I don't have to make it. I don't have to order it. I don't have to receive it. I don't have to store it. Nothing has to be done if a part does not exist. So, minimize information content is generalizing that concept of reducing part count. It's keep it simple. Don't have weird shapes. Like, somebody says, okay, well, how about this nice curve? But who's going to manufacture it? It increases manufacturing costs. So, I had the whole slide on that. But either way, so we've talked about these points. Functional requirements address intent and behavior during operation. Many functional requirements are possible. Da da da. So here, just the independence of functional requirements, I have an example for this. We've talked about it enough, and I think we had a more fruitful conversation here in the slide here. But the thing here is that, let's say you have a stapler and you have these functional requirements: impart enough force, bend the staple once it reaches the other side, and ready the next staple for the next round of stapling. If we incorporate the electromagnet, the ability to ready the next staple is affected. Now you have dependence, right? And your dependence, now one affects the other, and that's a bad thing generally. Minimize the information content, number of parts, okay? If you can reduce a part, eliminate a part, that's always a good thing, okay? Number of assembly steps required. So if you have a lot of assembly steps in a product, you will say, okay, well, number one, it's going to take time. You need training of personnel. You need to do it in the right order. You can make mistakes. All those things can happen, right? There's a course that I teach in design for manufacture where some of the examples are just so ridiculous, it's crazy. That Boothroyd gives an example of an electrical assembly where they went from, I don't know, by a factor of 50, they saved the time in assembly because they reduced part, they simplified things, they have standard connectors. Imagine soldering everything together versus just a connector, snap connector, and now you connected 50 things together. And so on and so forth. Number of different material types. So that's been considered a challenge in not only manufacturing, in disassembly and reuse and recycling as well. If you're using different material types, now somebody has to make this, they have to be sourced, they have to be done a certain way. How about we combine them into one? How about we use the same material for everything? Or something that's benign. So sometimes it evens out. So you'd say, okay, well, I need this material for this because it's corrosion resistant, but I need that material for that because it's structurally better. Okay, or I have a third material that is more expensive but can do both. Sometimes it's better to have something that's more expensive that can do both because now you have simplified certain things, right? Number of fasteners required. These I'm just giving you examples of what you should think of when you think about information content. If you have too many fasteners, that's a problem. If you have too many parts, that's a problem. If you have too many assembly steps, that's a problem. Average assembly time, number of machining operations, number of different dimensions used. So talk about part standardization. In a design, standardize things, right? So once you get down to subsystem component level, now you'll see the same parts. You look at the circuitry and the controllers and the relays in an aircraft, pretty much standardized parts. You part number so and so from this company, and you order 30 of those. So these are just examples, but then by now you must be thinking they have to conflict. On the one hand, I'm saying that keep them separate. On the other hand, I'm saying no, minimize the information content, which usually happens when you combine things, right? So, so it's a challenge that we all face, and those are the things that are the that require iterative design. That we think about a design, and then we said, okay, we minimize the information content, but we lost the independence of functional requirements. Where is that line, right? And that's why we talk about iterative. You do it, and then you figure out what can happen. So let's say after 10 years, you realize that my repair and maintenance steps are too complicated. Then you think of, okay, maybe we should separate these because it didn't work out. So an example I gave is like the front fascia of an automobile where you have integrated fog and turn lamps, right? So one lamp has fog lamp and turn lamp together. Well, if one breaks, you have to change the other one. That breaks, you have to change this one. It affects the other ones, right? So you can make it simple, but repair causes issues, right? And in case of a minor accident, let's say something that damages one light, now you have to change the entire assembly because it's just one single assembly. It was easier to make, but now you have paid the price in the cost of repair and manufacture or replacement. So independence of functional requirements can and does interfere with minimum information content axiom. There is no way around it. And I think that you should also study TRIZ, theory of inventive problem solving. I don't know if anybody has heard of TRIZ. So TRIZ was a method was proposed by a Russian scientist who said that once you start improving designs, eventually you start seeing conflicts. If I do this, that happens. If I don't do it, this happens, right? So, or two different things conflicting. So he said that most engineering design problems can be categorized into 40 different problem types. Okay, so in TRIZ, you convert a problem to one of the TRIZ problem types and find a solution, and then you convert it back to your problem per se, right? So when you use a solution method like that, you will start seeing that why certain designs, if you want to improve a certain design, you can create independence, or you can actually get rid of independence and come up with a better design. So TRIZ is something that you should definitely study. And like I said, these two axioms conflict more often than not. Again, I would say that there cannot be hard and fast rule, but more often than not, my view is independence of functional requirements supersedes the minimize the informational content of the product. Okay, so you can try to minimize functional requirements, minimize the dependence of functional requirements, or maintain independence of functional requirements, and of all those designs, minimize the information content. Okay. Okay, so that's that. The next one is just a quick run through of what we have already done, and then we'll go from there. Okay. So a chemical scrubber example. Do you know what a chemical scrubber is? So think of chemical labs or things like that when you do experiments and then you release certain chemicals, gases, so on and so forth. You cannot just release it into the environment. They have to be turned benign before you can release it into the environment.
So do a lecture if you want.
But we took a break, right?
If you want, you can stop at 7:20 or whatever.
Okay, so basically these are systems that render harmful chemicals harmless. Okay, this catalytic converters, but these are like specific ones that we use in large installations, right? So there's pyrolyzing ones that actually force the chemicals to react with other chemicals so that they become inert. Sometimes they're just like, you just run them through water and then that scrubs the material, right? So these are pollution control devices. They will take chemical vapor, spent gases, particulates, and then render them harmless. So, and it's okay if you don't know what a chemical scrubber is. The idea is to learn how to make something new, right? So, needs statement. So, consider a company that has just received an order from a customer to manufacture a chemical scrubber. The customer is located in India. So, this is, imagine that you're in the US right now, okay? And requires the scrubber to only treat relatively harmless gases which only need to be washed with water. The customer cannot guarantee that, no, this is verbatim. This is, let's say somebody sends an email to you, okay? It's intentionally written in a more conversational but less technical way. The customer cannot guarantee that there will be continuous water supply for the scrubber, but does guarantee uninterrupted power supply. The amount of gases to be scrubbed is significant, and the experiments do not impart any pressure to the gases, so the scrubber should be able to create suction. The customer also wants the scrubber to provide visual or audible signal in case of a malfunction. In addition, the customer provides a layout of the lab the scrubber will be used in along with gases to be scrubbed. Okay, so you have to parse this into needs statements, right? They will send a paragraph like this. One little comma, one little phrase could have huge implications, right? So if they say, cannot guarantee that there will be continuous water supply. Well, you need water for the scrubber to work. But yes, but the concentration of chemicals will go up. So maybe you can store water in the scrubber to store fresh water, and then a lot of these things are interrelated. So you'll see that in a second. Okay. Okay. So we rewrite these in a standard way, which is the customer needs to, or the scrubber needs to have this, and the scrubber needs to be able to do this. And then we need to develop a basic understanding of the functioning of the chemical scrubbers, right? So don't start designing things like this without learning a little bit about it. Okay, so talk to your expert, talk to the expert in your group, hire consultants, or perform literature survey of existing chemical scrubbers, right? How do other people do it? Some of these designs have been existing for 50, 60, 70 years, right? And then it said that, the customer provides a layout of the lab along with the gases to be scrubbed. So they provide what sort of chemicals they're going to release. So now you can plan accordingly. Okay, this much chemical, so I need this much flow rate. Or you can actually tell the customer, a simple scrubbing with water will not work in this case. Okay. So we just try to parse what the customer said. Since the location is in India, the scrubber's electrical system should be able to handle 220 volt power supply at 50 hertz. In the US, it's 110 volts with 60 hertz at 60 hertz. So this actually was the problem we were working on. So the first thing you have to say that everything you buy, either put a transformer in there to go from 110 to 220, or every single electrical component in the scrubber has to be able to handle 220 volts. Okay, you don't do that and bad things happen. Another thing is that then you have to also think about efficiencies, because motors that run at 60 hertz or designed for 60 hertz will run at a lower efficiency when you give them 50 hertz. Okay, so all those things have to be thought of. You cannot ignore it. And so generally what you would do is that you when you order the individual parts, you always look for voltages and frequencies. Can it handle 50 and 60? Some 60 hertz will not work at all, or they're not designed to work on 50 hertz. So those things have to be thought of. The scrubber needs to be able to generate suction. So then you have to do some analysis. Like, they said the layout of the lab is this. This is how far the experiments are going on. The experiments don't impart any force, so you have to generate suction, right? Some negative pressure so that you can actually pull those gases towards the scrubber. And then obviously needs to be able to read the amount of gases released. You say, okay, well, they say we're going to be running 6 experiments simultaneously. And then you do the calculation and go, oh, we need to have a big scrubber or 2 scrubbers or something like that. And so on and so forth, right? So amount of quantity needs to be known, layout of the lab needs to be known. We assume that 5 inches of water column, and don't tell me why the pressure is used in inches of water column, but pressure can sometimes be measured in inches of water column, right? So atmospheric pressure is how much water column? Anybody know? 760 mm of mercury, 10 and change meters of water. So basically you can say, okay, that's just a unit they're using. You could work with just as easily with pascals and so on and so forth, right? Or PSI or whatever you want to use. That's not critical here. But whatever pressure that needs to be generated so that you have done the calculations that given the lab layout, you'll be able to pull those gases to the scrubber. And then a packed tower would be used to scrub the amount of gases encountered. So think of it this way, that you have essentially a tube, a vertical tube, where you have put a lot of plastic balls, or basically you're trying to increase the surface area. So basically you flow all the gases from the bottom, and from the top you spray water and the water trickles down, and then it has a lot of surface area to interact with the gases, and it scrubs it, right? Again, I'm not a chemical engineer. I'm not talking from a scientific standpoint. I'm talking from a systems engineering standpoint. Like, if you were to design something like this, what would you do? Okay. You might consult a handbook of these things to make it. But as an engineer, as a systems engineer, you still have, your work is not done just because you figured this out. Putting it all together is our job, right? How to make something like this that works as an integrated unit. So need statements. That's pretty straightforward. The scrubber needs to generate suction pressure of 5 inches of water column. Needs to have packed towers for scrubbing. Needs to function without continuous water supply. Needs to have warning alarms in case of a malfunction. And needs to accept 220 volt power supply at 50 hertz. You can draw your house of quality. I'm going to leave it to you to do this. And this is not an exhaustive list. I mean, you can probably come up with more needs that I did not write down. Okay. So the functional diagram is like this. You accept electrical energy. So that's the dotted lines, or I should say the dashed lines. Accept electrical energy at 220 volt 50 hertz. Convert energy to kinetic energy of water and to create suction. So since you have to create suction, you need to use power to do that. You need to move water. You need power for that. Okay, so think of it this way. So you accept flue gases and accept water. So when you create the suction, you're able to accept the flue gases. You measure the suction pressure, because if the suction pressure is not high enough, then maybe there will be backflow, and that's dangerous, right? Because we're talking about harmful chemicals. So, and then you run the water through flue gases and reject inert water, gases, and water. Okay, so you rejected it. Accept water, store water until need to replace, because the customer said they cannot guarantee continuous water supply. So you store water, and then you measure water pH and measure water level. So you have to have enough in the tank that you can run the system, and then you have to have another tank, or you can have this. You can run the same water through the tank, but as the concentration builds up, maybe the pH of the water changes, so you have to have a sensor. So whenever water level goes below a certain level, because of evaporation or something like that, or when you're rejecting it, whenever water pH goes above or below a certain number, whatever you decide is safe, and whenever the suction pressure goes below a certain amount, you sense malfunction and you set off alarm. So we were talking about safety, adding safety. You can add safety in this way. There's a feature that sets an alarm. So in this particular case, it could be something like, oh, our water is already too tainted. It will not accept anymore. You should not be running any more experiments. It starts beeping, right? So people should not be running experiments. We don't have enough water left, so we need to replace those kinds of things. So, and then you need to have some sort of intelligence, right? I mean, most of these can be controlled with a simple PLC. That you can take all these inputs and you say, okay, this is below that and that is below this, so take this step and whatever. You can have as advanced as possible. You can. It's totally up to you. Oh, so basically, I went through this anyway. Measure suction pressure, measure water pH, measure water level, and then reject inert water, sense malfunction, and set off alarm. So this is just the steps. So concept generation. Let's say accept electrical energy at 220 volts at 50 hertz. Okay, that's trivial, but needs to be done. Things will break. When my wife took some of our electrical stuff to Europe, that's also 220 volts, at least similar. And some of those things did not do so well. Right, so pretty straightforward. Make sure that all the components within the scrubber's electrical system are compatible with it. You could also make the decision that I'll have a transformer and use all the standard US components, right, that work with 110 volts. That's one solution you could come up with, but now you're talking about space. Or you could just buy different components, up to you. Convert energy to kinetic energy of water and to create suction. How will you do that?
Some blades.
So you need to have some pumps, you're saying. Right? Pumps. What kind of pump? Water has to move and air has to move, right? Because you have to somehow create suction for the flue gases, and you have to also pump water from the tank, wherever you're storing it, to all around, so you can spray it or whatever through the flue gases. So 2 pumps, okay? 1 pump for air, 1 for right. So let's see. We use a water pump, let's say, right? So first we have to use a water pump to move the water from the tank to wherever it needs to be sprayed. You use a centrifugal pump, you use a vane pump, you use a peristaltic. You can use all sorts of pumps. There's really some of these are bad ideas, but in the beginning you don't think of it like bad or good ideas. You just do it. And then evaporate. Another one could be, we can evaporate water by heating and let steam flow through the flue gases. I mean, you can do crazy things. I mean, this is brainstorming type sessions. So, and then the other one is, do not use electric power to move water. Store water above the scrubber and then let gravity flow through the flue gases. So one thing I could also do is that instead of putting the tank here, I could put the tank on top of the scrubber. So the water automatically flows down, right? Well, that's a bad idea. Why? We cannot control the gravity, but we can count on it, right? We know how much it's going to be. Well, first and foremost, if you have a finite amount of water, it will eventually run out. The customer said they cannot guarantee we'll have water all the time. So that's a bad idea given the constraints that we have from the customer. So we need to be able to, and once it falls, we need to be able to reuse it with a pump. No matter how you do it, you need some way of moving water, okay? So that's a bad idea. How do you accept flue gases? So I give you a huge pipe. On the other end, chemical experiments are going on that release fumes. How will you accept it here? You'd have some sort of pump, right? So first you assume that it's going to happen anyway. Sometimes people do that. That's a bad idea because the customer said clearly that they don't impart any force over there. You have to create suction. Use an air pump. You can use that. What can go wrong there? Oops. Well, one of the things we talked about is that these are chemical experiments, right? You don't know what's coming out the other end. Either you buy a pump that can tolerate toxic chemicals or corrosive chemicals. In fact, there's ratings for those. Like all pumps, you can buy those things. Those are an arm and a leg, very expensive. But you can say, I want something that can handle acidic fumes or something like that. And then you can buy a pump like that. But then that is a challenge. Things will get damaged very quickly if you're working with corrosive things. You can use a fan. You can use a venturi, and I'll come back to that in a bit. And then another one is like some crazy ideas. If I cool things, then it creates negative pressure and things cool down. Oh, I don't know if it'll work. So we have these ideas, and then we also have a caveat that brainstormed ideas don't always have to be feasible. You don't have to say, oh, that's a bad idea. You say, no, hang on, think about it. Maybe it's a good idea, or it has other benefits, right? So, I mean, just as a bizarre extension of this idea, if I'm cooling something a lot, I can condense air from the water from the air. Maybe I don't need continuous water supply. When you can think along those terms, maybe it will be feasible, maybe it wouldn't be. In high humidity areas, maybe it'll be feasible, right? So, okay. So then convert energy to kinetic energy of water and to create suction, except flue gases. I can maybe combine these two things into one, right? So going against my functional requirements thing, but you'll see how magically things get better. Okay? What about it? Using a water pump with a venturi. So now, I look like I'm violating the independence of functional requirements. But the benefit I'm getting is immense, right? So now, so this is a cross section of a venturi. I take high pressure water from the pump and I spray it in a nozzle like that, right? If you spray it with a high enough velocity, it creates enough suction that on the left hand side, the flue will automatically be pulled in. You can do this experiment. I build these things with my own hands. You can create some serious suction that way. Okay? And the location of the nozzle, if you move it higher or lower, you can change the pressure generated. Now think about this, right? If I'm just spraying water, I don't have to have a pump for the flue. All those parts and electrical connections and all those things, so I minimize the information content. I have no moving parts in here. It's just a basic thing that sits there. You spray water and it pulls the flue gases in, and then it scrubs them too. So even here, because the water is so atomized as high pressure that when flue gets pulled in, it already is mixing with the water. So some scrubbing is already happening. So it solves so many problems in one go. Okay, and all I need is a water pump. I don't even need an air pump for this, right? So we can use it, make a PVC because it's relatively inert to chemicals. We spray water through this, and then there's a decreased cross-sectional area. So the energy for the suction is indirectly supplied by the water pump, right? So you're stealing some energy from there. So you also are performing some scrubbing here. It, however, increases the required power rating of the water pump, right? So earlier you could just get a tiny little water pump. All it has to do is just spray water, collect it, spray water. Now you have to inject it through a small hole in the nozzle with high enough velocity that it can suck flue gases, right? So now your design requirements change. So there was dependence as you would talk about, right? So that is solved for now. Run water through flue gases. So you can do a lot of things here. You could say, I can have pipes and I can spray water. Well, the customer essentially asks for a packed tower. So this is a common thing. Like, they'll say, no, we want that. We don't want to compromise on that. So that's okay. Well, then that's what we'll give you, right? We need to determine the size and type of packing. How thick should the tower be? What sort of things should be inside so that it increases the surface area. I mean, we use plastic balls sometimes, and then and they also work better when there are particulates present. So maybe the customer thinks that there may be particulates in the air, right? So that's why they said that. And this is pretty standard. Measures pressure, off-the-shelf fittings and sensors. You can buy these fittings online. Standard connections, PVC connections that you have at home. Measure water pH, measure water. All this is pretty standard stuff that you can buy online. So there's really nothing there, but you need to know where to get them and how to install them. Okay. Store water until there's a need to replace. Tank. Where do you store water? In a tank, right? So, water tank. Okay, so this is the standard setup for the Venturi scrubber. You have a water tank right here, and then this thing takes water, pumps it through this. Some of the water is trickling down this packed tower, which is just a column where you have packing, which is just like little plastic things that you stuff in there so that it increases surface area. And then most of the water, or some of the water at high pressure, is going through the Venturi. That's creating the suction, and the flue gases come in. You have a pressure gauge there, and then all that falls straight into the same water tank, right? Over time, water level might change, water pH might change, and then when something goes wrong, it senses and then sets up an alarm. And then every once in a while, you drain the water and replace with fresh water, or when there's an alarm, you replace with fresh water, right? So this is pretty. An engineering student would probably, if you have all the parts available, you could probably assemble the whole thing in a day, right? So it was pretty straightforward. I mean, we made complex ones too, but this is a pretty standard one. But again, like, this is more or less like a system. You got to see conceptual design, how to come up with solutions, how to think about minimizing information content, maximizing independence of functional requirements, and so on and so forth. So come up with something that you can actually sell. So these things are very much in demand, and now you know how to make them.